Welcome back. We're in section 12, the final section in chapter 20, and we're going to talk about the synthesis overview. Now, a lot of these reactions you can memorize, you can work through the curved arrows, but here this is just focusing on synthesis, which is of course not just one-step reactions, but 2 or 3, okay? Possibly 4 or 5. So we want to talk about these reactions in red. These are the new reactions that we've just learned that react ketones or aldehydes with different stuff, okay? But we also know about alkanes, alkenes, alkynes, alkyl halides, and alcohols. These highlighted green boxes are like international airports that have many different reactions going in and many different reactions going out. I would like to add some reactions to this sheet so that you'll fill in your knowledge gaps as necessary. To go from an alkene to an alkane, that's the most simplest reaction. It's hydrogen with a platinum catalyst. To go from an alkane to an alkene, you might need to do a couple of different things. You might have to introduce a bromine atom using radical bromination, and then do some kind of elimination reaction. Okay, and there's all kinds of rules and different, cis and trans, all that kind of stuff I'm not going into. To convert an alkyne to an alkene, there are several different ways of doing this. I'm just going to do sodium and liquid ammonia. To go from an alkene to an alkyne, you're going to have to do halogenation and then treat that with, excess base. And to go from an alkyne to an aldehyde or a ketone, there's many different ways of doing that. One is to do a hydroboration, okay? Another way to do it is hydration, and you have to use mercury in there. So anyways, I'll just leave off the step 1, step 2, because this is just a one-step reaction for the mercury. So again, you might, if all of these are like foreign, you definitely need to flip through your flashcards and kind of remember them. So we've talked about this reaction in this chapter. We can add LAH, okay, followed by water. We can go from an alcohol to an aldehyde or a ketone using PCC, for example. Alkene to an alcohol. We can do something like this. Alcohol to alkene, H plus heat, HBr, base, bromine and light, or X2 and light. Okay. Now, those are all old reactions that we've talked about through the first semester organic chemistry and a couple of them in this second semester organic chemistry, depending on the pace of your course. All of these reactions, what are those reactions? Do I have a list of those? Well, in the back of the textbook, they have a review of reactions, as usual, at the back of the chapter, and they have these 15 different reactions that you should put on flashcards and memorize, okay? So in my course, we've talked about 1, 2, 3, we've skipped 4, we've skipped 5. We've definitely talked about 6, 7, 8, 9, 10. Where's 10? No, we skipped 10. 11, 12, 13, 14, and we skipped 15. Okay, so if you're in my particular class, you know me, you're taking my course, skip 4, 5, and 15. But these are the reactions at the end of the Klein's book. Put these on flashcards, work through them, know them like the back of your hand, so that you can do more synthesis problems more carefully, okay? Now, in the textbook, they just give you lots of different ways of analyzing things, and as usual, their synthetic advice is the same. Step 1, is there any change in the carbon skeleton? Are you adding carbons or removing carbons? If you are, there's only a handful, 3, 4, 5 reactions that we've learned so far that make new carbon-carbon bonds, okay? And then number 2, is there any change in the functional group? That's this page I'm showing you right now, right? All the functional groups are changing, okay? Definitely have a handle for this map here. Okay, if you're starting your drive out with the alkene and you want to end out somewhere else, kind of know what functional groups are involved. Okay, so that's the advice that the textbook gives you. There's not a whole lot of examples I can show you here, so I'm just going to do some problems. And remember again that you can find tons of these problems online or in the textbook. I'm going to do problem 41. 42 is a great problem, and your textbook says try problems 55, 58, 67, 68, 69, 71, and 75. So this is a big emphasis for this chapter, okay? You might think at first it's curved arrows, but actually it's more about the synthesis and predicting products and how do you go from A to B. That might be more important for your professor and what they emphasize in the course, okay? Now, let's go ahead and do problem 41 here together. Okay, this is problem 20.41. I haven't scripted this, of course. I have not scripted this, and I haven't even looked at these, okay? This is the first time I'm looking at it. So maybe I'll get stuck. Maybe I'll hit a roadblock. That is certainly possible. You have to take a break and come back to it. These are not problems you want to do the night of the due date. Let's just go ahead and work on these, okay? So in problem A, what am I noticing? Well, I'm noticing that I have no functional groups in my molecule, so I'm going to have to introduce a halogen. And I know that a halogen is going to pop in at the more substituted carbon. Now, when I look at the molecule that I'm going to make, I see that I have a double bond here. And there's an additional carbon that's being formed on an alkene. And I know I can make alkenes from Wittig reagents. So we want to work backwards, believe it or not, which is kind of strange to think about. But we have our alkene, okay? And I want to think about this possibly coming from a ketone. Okay, that's a three-step procedure to make an alkene from a ketone. And then I just want to think about, well, how can that possibly, where do ketones come from? They come from alcohols, right? Where do alcohols come from? Alcohols come from alkenes, okay? And where do alkenes come from? They can come from alkanes. We just talked about that in the previous slide. So for the synthesis here, I'm going to, okay, so before I jump into this too much, I just want to emphasize I'm dealing with functional groups here. I've got an alkane, I've got an alkene, I've got an alcohol, I've got a ketone, and I've got another alkene, okay? And so this chart right here kind of helps you chart out your flight path so that you can kind of do it. And then you have to recall the individual reactions for each of those individual steps. So I'm going to go ahead and do the synthesis now. I have my alkene. I'm sorry, alkane. I'm going to treat this with bromine and light. And that's going to make my alkyl halide. Okay. And then I want to do an elimination reaction using sodium, ethoxide or something like that, nice base, to give me my alkene. Now I need an alcohol. I need the anti-Markovnikov alcohol, so I'm going to add borane THF, basic hydrogen peroxide, I'm not going to draw the stereochemistry there. It's not really important for this problem. So now I've got my alcohol. Now how do I make a ketone from this? I can add PCC or the Jones reagent. The Jones reagent is sodium dichromate, sulfuric acid, water, acetone, all that stuff. Or just write Jones if you're in my class. And that will make our ketone. Now from the ketone, we want to go ahead now and form the Wittig reagent. So off to the side here, you might do that separately. I need to add a methyl group or a single carbon. So I'm going to add triphenylphosphine, bullethium, and then that ketone that I just made over here, okay? You see, I can't just keep going with the arrows because I need to stop and say, okay, we're going to meet up and then converge here. Okay, so that's going to be this ketone, and that's going to give me the product here. Okay, so that's 1, 2, 3, 4, 5, 6, 7, or 5, 6 different kind of functional group steps. 4 steps, right? So when we look at the molecules here, you should see that A and C are highly related. If I look at molecule C and I think backwards, this looks like an alcohol. How can I make alcohols from aldehydes or ketones or things like that? I need to realize that that's a methyl group, and I can synthesize that from this ketone and a methyl Grignard. Okay, how do I make that ketone? Well, I've already made it in problem A, so the textbook is kind of being very generous for me. If I figured out all of that, then I could just do the last step. So in problem C, I can do the first 5 reactions, C problem A, and then the last step is going to be taking my ketone, adding methyl magnesium bromide in step 1, and then step 2, add water, and that's going to form that target molecule that I'm interested in. Okay, so there's not a whole lot to figure out there. Okay, now in molecule D, you can see how I'm starting with the same starting material, and I'm making this thing right here. What? It's opened up, right? So if you think about what can open up molecules, we're thinking about maybe ozonolysis. Okay, if you just think in a forwards direction, if I treat this with ozone, right, zinc, a little bit of mercury, H+, this will open it up to give you, a dialdehyde. For example, so that might be something to think about. What other reactions have we seen that can open up the ring? I think that's it. So if we're doing problem D, let me create a new image of this one. So let me think carefully about what I want to happen here. So this portion here looks goofy, all right? I don't have a ketone there. But here's a methyl group, right, that seems to be added to that. So I could think about retrosynthetically, maybe that could come from this, ketone. Okay. I could add a methyl group or a Grignard reagent to a ketone. And then this, if I zip it up into a ring, right, do retrosynthesis for the ozonolysis, that possibly could come from, you see, this is a 1,6-diketone, so that's going to come from a 6-membered ring where there's a double bond. I'm numbering it wrong here. Between carbons 1 and 6. Okay. Carbon 1 has this methyl group. Carbon 6 has this methyl group. Okay. So it might even seem harder to make that molecule. How do I go from that to that? Okay. I can see some ways, and it's just very pedestrian, meaning it's going to take many steps to do that. But here again, I'm just focusing on the retrosynthesis, not getting the right answer and making you see how you go from A to B to C to D to E to F to G to H to I. So anyways, retrosynthetically, this is a reaction that you've seen before. You should recognize that's a way to break open a ring. And now the problem becomes, how do I go from here to here? and then how do I put on, you know, a methyl group or something, right? How do I get this boxed methyl group onto that ketone? Okay, so this is an incompletely solved problem, but you can think about that. Problem B looks different enough that, you know, maybe we should talk about that. Okay, so this is problem 2041 as well, part B, and I'm going from my alkyne to this weird looking molecule here, okay? And first we want to count the carbons to see if anything's going on. So, you know, we got the 6-membered ring, and then we've got these 2 carbons out here. So here I have my 6-membered ring, and I've got my, well, I've got 3 carbons, don't I? I have 3 carbons, so I need an additional carbon, and I need that carbon to be added right here. So, you know, how do I do that? I'm not sure. I don't see how I could do that. But one way that you could think about how you know, where do alcohols come from? They can come from alkenes, right? So that might be something to think about. But the carbons are weird, so how do I get that 3rd carbon on there? Alcohols can also come from ketones and aldehydes. So there's an aldehyde. Alcohols can also come from alkyl halides, but I don't see really much use in that. Let's go ahead and just sketch that down. So what I'm doing here is kind of focusing on the, you know, the functional groups. But what I really need to focus on is the carbons. How in the world do I get an additional carbon in there? So you want to think about the different ways that you can form carbon-carbon bonds. One way to do that is through Grignard reagents, right? Grignard reagents react with ketones, aldehydes, epoxides, stuff like that. So that might be one thing to think about. This is a puzzle, right? It's a puzzle. So, but normally when you react a Grignard with a ketone, okay, so if I want to add a R group to this molecule, okay, that's going to add right on the same carbon that has the hydroxyl group. That would add here. You know, if I, you know, here I want to add it there. So if we want to do retrosynthesis, we would have to say, well, this can come from you know, like a yeah, I'm just stuck on this one. I'm sure I could look it up in the book and it'd be obvious, but that's not very educational. So I'm stuck on this one. I don't know how to do this problem because there's probably like 1 or 2 ways to do this, and I don't immediately see the way. Okay, I'm probably just forgetting a reaction. I haven't gone through these well enough to know. I'm thinking epoxide, but that would give you the different regiochemistry. So now if you think about in the forwards direction, you might think of different reactions you can do with an alkyne. So what we can do here is we can you know, convert this to an aldehyde or something like that, or a ketone. So we can convert this to acetophenone with an ordinary hydration. I shouldn't put step 1. That's the only step. Mercury, acid, water. Okay, so this will make a ketone. And then I could add a Grignard to this, right? I mean, I could add my more carbons to it. So if I add CH3 MgBr for example, and then I add water. This will make a molecule that has an alcohol here, but the additional carbon is going to be connected to that same guy there. I mean, I guess you could do it this way. I was just expecting it to be kind of shorter. Now I see a relationship between this alcohol and this alcohol. They have the same number of carbons, but they're different regioisomers, or different constitutional isomers. So I need to get this alcohol from that carbon onto this alcohol of that carbon. So what I could do is treat this with acid and heat, right, to make the alkene. And then now I see the relationship. I need an alcohol at this carbon here, so I'll now treat this with the hydroboration procedure. And that will get me the target molecule. So I turned out to be lucky. As you can see up here, I did think about the correct alkene that would solve this maze, but it was so many steps in, I didn't quite see it, because this alcohol has the hydroxyl group in the wrong position compared to that. So I wasn't thinking about that kind of trivia that the book kind of puts forth once in a while. All right, so the problem goes on, E, F, G, and some other stuff. So let's do E and F. These seem relatively easy, so let's do, okay, in problem E, we definitely have an imine. So this, you should know from this chapter, this comes from an amine and a ketone or aldehyde. In this case, a simple cyclohexane carbaldehyde, and the amine is going to be isopropyl amine. Okay, and then now we need to think about how do we go from that alkene to this aldehyde. Gosh, I don't know. I mean, there's an additional carbon there, right? So if you count, well, I don't know how you really count this really well, efficiently, the best way, but there's one carbon out here, and there's one carbon out here. Oh, it has the same number of carbons. So you see how it's important to count there. So what I need to do is think about how aldehydes can come from alcohols, and alcohols can come from alkenes. Okay, so this problem is maybe more relatively straightforward, at least for how my mind works. So in the forward synthesis, we're going to then, go this way, right? In the forwards direction, we're going to take the alkene given to us. We want to treat this with borane and hydrogen peroxide, sodium hydroxide, and this is going to give us the anti-Markovnikov less substituted alcohol. Alcohols can only be converted to aldehydes using PCC. If you use Jones, you'll get the carboxylic acid, so don't use Jones. Once we have our aldehyde, then we can treat this with isopropylamine and a drop of acid as the catalyst. Okay? So that was much shorter, 3 steps. Let's look at problem F. In problem F, we have an aromatic ring, and we're sticking 2 stuff on it, right? So halogens, we know, is bromine and iron tribromide. And how do we get this carbon thing on there? Well, this is where you need to think back to the Wittig reagents. The Wittig reaction can make alkenes directly from ketones, and now you should be able to do retrosynthesis on this. Okay, this is a meta-substituted molecule, so we want to keep the substituent that is a meta-director. Remember that Ketones and aldehydes are meta-directing, and that can come from your benzene. Okay, so in the forward synthesis, we want to start off with benzene. Okay, we want to do a Friedel-Crafts acylation. This is chapter 19 material, by the way. So there's 5 reactions you've learned, but there's a lot of details there. So this is the correct acyl guy here. Now, if we treat this with bromine, and don't forget your catalyst, iron tribromide, this will give us the metabromous propiophenone, I guess it would be called. Now, from this, we can do the Wittig reagent reaction to get the product. So I'll just put Wittig. Okay, I don't think you'll get much benefit from me writing out the 3 steps that you've just seen before in the previous lecture. So yeah, so the book has these kind of trivia questions here. Problem 42, I wouldn't recommend just starting off with, because you're supposed to start with only 2 carbons, and then the molecule might have 4 or 6 carbons. So it's just like a lot of busy work to synthesize those. It's not very practical, but it's good for memorizing reactions. I would jump to the try problems and try problems 55, 58, 67, 68, 69, 71, and 75, where it says try problems in the book, okay? I'm skipping section 13, which is spectroscopy, but the back of the book has excellent practice problems, and I urge you to work on those on yourselves. Thanks for watching. We're done with chapter 20 now.